This is section 4.2, extreme values. We're going to split this lesson into 2 days, day 1 and day 2. So on the first day, we're going to really focus on maximums and minimums and what critical points are. Tomorrow, we'll talk about absolute maximums and minimums and discuss what it means between those critical points. So for example 1, we're going to jump right in. Identify the x coordinates of each of the following for the graph of f of x to the right or the graph below. So we want local maximum. It's exactly what it sounds like. Your maximums are the high points. So here's a high point, here's a high point, and here's a high point. I didn't ask for the y values for these, just the x values. So you can tell me that the first one is at 1, 2, 3, 4, 5, -5. The second one is at 0, and the third one is at 2. We next want to find the relative or local minimums. Where do those happen? Those are the low points. I just did the wrong maximum, didn't I? Let's get rid of that one. That's not a maximum. This one is. I'm half asleep this afternoon. My maximum's over here at 1, 2, 3, 4. All right, let's try again for the minimums. So the first one's here at 1, 2, 3, -3. This is another minimum over here at 2. So we have our maximums, we have our minimums. The intervals where the function is increasing. This is where you want to use that interval notation you learned in pre-calculus. So we are increasing from here to here. We're going to say -∞ to -5. The next place where we are increasing is -3 to 0, right along here. Use that union symbol. And then we're also increasing from 2 to 4. The intervals where the function is decreasing. So we're going downhill between -5 and -3. We are also going downhill between 0 and 2. And we are going downhill from 4 to infinity. The next thing we need to know is any locations of a horizontal tangent line. A horizontal tangent line would be where we have a slope of 0, where it's horizontal. And I'm going to work right to left on this one. So I definitely have a horizontal tangent line over here at x equals 4. We have a horizontal tangent line here at x equals 2. Switch the order. I have a horizontal tangent line here at 0. And I have a horizontal tangent line here at -3. Now, this point right here, saved him for last. I do not have a horizontal tangent line. This is called a cusp. At a cusp, the slope is undefined, or the first derivative is undefined, not a horizontal tangent line. So we're going to say undefined slope at x equals -5. So what I'd like you to do is use those same ideas, take a minute and try them with this graph to the right. Pause the video if you need to come back to that. All right, so we are going to look for the local maximum. Where does that happen? Happens right here where x is equal to 0. Your relative or your local minimums happen down here where x is equal to -4. And over here where x is equal to 2. That's your local minimum. The intervals where the function is increasing. So increasing is going uphill. We're increasing between here, -4 to 0. And then we are also increasing from 2 to infinity. Intervals where we are decreasing, -∞ down here to -4. And then we're also decreasing from 0 to 2. Horizontal tangent lines, we've got a couple of those here. Your horizontal tangent lines, again, are where that slope would have a horizontal line here, here, and here. We've got 3 of them in this case. -4, 0, and 2. I don't need that parenthesis over there. Then undefined slope, that happens at a cusp. I don't have any cusps in this picture, so that does not apply to us. There you go, maximums, minimums, increasing, decreasing. Now, on the next page, critical points. Everything in the rest of this unit is based off of the lesson before, so critical points are very important. Critical points are the points in the domain of the function f at which f prime of x does not equal 0 or it does not exist. So what we need to do is calculate those critical points. So what we are going to do is take our function, got to find the first derivative. So f prime of x is equal to 3x squared minus 18x plus 24. Once you have the first derivative, you set it equal to 0. So 0 equals 3x squared minus 18x plus 24. At this point, your job is to solve for x, so you need to factor out a 3. And then we need to factor what's inside. This is where you remember your algebra skills. This is my Algebra 1 lesson this week. Minus 2. And minus 4. So my solutions are x equals 2 and x equals 4. Those are the two values where the first derivative would be equal to 0. Those are the critical points. That's important to keep separate from inflection points later on, which are going to have to do with the second derivative. But right now we're just dealing with the first derivative. So let's try again. Find the critical points for this function. Now this one's a little bit different, it has that square root in there. Now, in order to find the derivative of that square root, that's a chain rule, if you remember. So this is 2x squared minus 2 to the 1/2. So with your chain rule, you bring 1/2 to the front, 2x squared minus 2. My new exponent is negative 1/2. This is the shortcut chain rule, by the way. Multiply by the derivative of the inside, which is 4x. If I simplify this, 4x times 1/2 is just 2x in the numerator. The rest of that slides to the bottom. 2x squared minus 2, still inside the radical. If I set this equal to 0, 0 is 2x over the square root of 2x squared minus 2. So not quite the same nice, neat algebra equation we had a second ago, but it's still very, very doable. Shrink this up a little bit. We are going to say that 0 is equal to 2x. Well, actually what we're doing is multiplying numerator and denominator by this radical. 2x squared minus 2, 2x squared minus 2. Well, what's anything times 0? 0. So 0 is equal to 2x. Divide both sides by 2. X is equal to 0. That is a critical point. But the other thing you have to worry about is the denominator. Where is this undefined? So we're going to have a second piece here. This time we set the denominator equal to 0. 0 is equal to the square root of 2x squared minus 2. Now, to solve this one for x, we square both sides. So 0 is equal to 2x squared minus 2. 2 is equal to 2x squared. And x squared is equal to 1. So x is equal to plus or minus 1. Now, this one has an added little twist to it in terms of those undefined places. You want to know, are they really part of the domain? And so that's a different question. If I put 1 in place of the x, 1 squared is 1, 2 times 1 is 2, 2 minus 2 is 0. I can't divide by 0. 0 is allowed inside of a radical. That piece is okay, but you can't divide by 0. So these two are actually not in the domain, but had they been part of the domain, they would exist. And this is kind of a gray area, open intervals and closed intervals. What you actually have at that point is a vertical tangent line. Let me see if I can show you real quick. Clear all this stuff out of here. If I were prepared, I would have had this in here already. So y equals the square root of 2x squared minus 2. There we go, looks something like that. If I shrink this down a little bit, you'll see that you have these vertical tangent lines at -1 and +1. So those are kind of sort of critical points. We have a bigger issue. What did we say the critical point was a few seconds ago? We said it was 0. But if you look, that's not part of the domain at all. This graph starts at -infinity to -1 and then picks up from 1 to infinity, but it doesn't exist at 0. So truly, this one's kind of a special example. Don't panic. The rest don't look like that. X equals 0, not in the domain. So the better answer in this one is plus and minus 1. But again, don't lose sleep on this one. We'll keep the rest to the easier algebra. But I just wanted to show you how to set the denominator equal to 0 as well. Find the critical points for f of x equals the absolute value of x. This one's easiest to look at the graph. Now, if I go back up here to my definition of a critical point, they're points in the domain of the function f where the first derivative equals 0 or does not exist. Where it does not exist. So if I go back to absolute value, f of x equals the absolute value of x, that is a picture that looks something like this. That's your V shape. And if you don't remember, just pop into your calculator, that's okay. So the question is, what's happening down here at this point? Well, that's the only place where the first derivative is undefined. Not that it equals 0, it's not a horizontal tangent line, but where the first derivative is undefined. And that happens at x equals 0. We have a cusp. F prime of x does not exist. It makes it a critical point. So the most common critical points are where the first derivative equals 0, and our textbook calls them stationary points. This other type, this cusp, is also a critical point where the first derivative does not exist. Now, these next two questions are a step ahead. They're really kind of for section 4.3, but I think we can talk about them. What happens when the first derivative changes from positive to negative? So when my slope switches from increasing to decreasing. Well, if I switch from increasing to decreasing, I have a maximum. If I switch from negative to positive for my slope, f prime of x would look like this. First derivative is negative, first derivative is positive. What happens when you switch from negative to positive? You have a minimum. So if I go back to that first picture that we had before at the beginning, there's a lot going on here. We can talk about this being a max. This one's a minimum. We mentioned that already. This is a max. This is a min. This is a max. Before we talked about increasing and decreasing. Now we can talk about, well, what's going on with the first derivative specifically. So in this region, where it's increasing, we would say that f prime of x is positive or it's greater than 0. That's another way to say it. Between here and here, we're increasing. F prime of x is greater than 0. From here to here, the graph of f is increasing, so f prime of x is greater than 0. If we look in the other direction, decreasing from here to here, this is decreasing on my f function. So the first derivative, f prime of x, is less than 0. In this region, we're also decreasing, so f prime of x is less than 0. Now here it's decreasing, so f prime of x is less than 0. Now, that new word for today, critical points, my maximums and minimums, where I switch. The first derivative switches from positive to negative or negative to positive. Again, we'll get into that in section 4.3. This one is a critical point. This minimum is a critical point. This maximum is a critical point. This minimum is a critical point. And this maximum is a critical point. So, increasing, decreasing, local maximums or minimums, and extrema. Extrema is that grouping word for maximums and minimums.